How's exam 2? Good. I like that. We'll get the scores up this afternoon. I'll post the key as soon as possible, but no later than sometime at the beginning of next week. Now then, what we wish to do is to show how, from fundamental thermodynamic considerations, we can perform a thermodynamic analysis on a reaction system, and as a consequence thereof, be able to understand what's going on with the reaction system thermodynamically. And with that, get at properties of the reaction system like equilibrium composition. Now, in the notes, chapter 21, you'll see this relationship given. This relationship can be derived from fundamental thermodynamic principles, but I have not taken time to do that. It's not in the notes. But if you go ahead and study some more chemistry, I am sure in any reasonably good physical chemistry class, you'll see this derived, this relationship. Q, as you might recall, which we considered in very brief fashion in chapter 17, and then revisited at the start of chapter 19, is nothing but a reference to an expression for a reaction which looks just like K, the equilibrium constant expression. So if you can write an equilibrium constant expression, you can write Q. What's the difference? The difference is the equilibrium constant expression pays attention to and includes exclusively equilibrium values, not Q. Q pays attention to any possible set of values for the system. And with that, allows you to make a prediction from a thermodynamic standpoint of the directionality of a reaction system. Now, this relationship brings together change in free energy for any possible set of conditions with standard change in free energy. We talked last time about what the standard state means. A specific set of reaction conditions. Gives us a more precise handle on the meaning of spontaneous. You may recall in 2045 laboratory, assignment 7, on solutions. We had you do some very simple investigations to try to get you familiar with delta G0 and what it means compared to delta G and what it means. For example, the sodium chloride dissolves spontaneously under standard state conditions and 25 degrees centigrade. The answer is yes. How do you find that out? All you need to do is to recognize that superscript 0 for solute species means concentrations of 1 molar. So if you take a solution in which the sodium ion concentration is 1 molar and the chloride ion concentration is 1 molar, like 1 molar sodium chloride solution, and you add to this additional sodium chloride and on stirring observe that the sodium chloride dissolves, you now know that whatever the equilibrium state is for sodium chloride with its component ions, in other words saturated sodium chloride solution, it exceeds 1 molar concentration. Upshot, delta G0 for solution formation of sodium chloride at NLC is minus spontaneous. Because you can get a concentration of the component ions which exceeds 1 molar. That's all there is to it. Now, Does calcium carbonate dissolve spontaneously in water? DIW at NLC. Does calcium carbonate dissolve spontaneously in deionized water at NLC? Think about this question before you answer it. It's question 21 in chapter 21. All right, time's up. How many vote yes? How many vote no? How many didn't vote? 10,000 points off from exam 2 for non-voters, which I will distribute amongst the ranks of those who voted. How about that? Talk about inequity. Woohoo! Do you know that you, in fact, answered this question by way of work you did in 2045 laboratory? Assignment 4, 2045 laboratory, experiment 4. You put together sodium carbonate solution with calcium chloride solution. Remember that? So as you made this mix, boom! Out fell this white solid, a precipitate. What was the precipitate? This stuff. Then by filtration, you separated the calcium carbonate you just made by precipitation and washed the calcium carbonate while it was on the filter paper to remove surface quantity of the sodium ion, chloride ion, and either excess calcium ion or excess carbonate ion. Then you're asked to take some of this cleansed calcium carbonate and stir it up into 50 milliliters of deionized water. At this point in assignment 4, you had already observed by conductivity studies that deionized water gives no conductivity reading whatsoever. Now, the gadgets we used to observe conductivity were not particularly sensitive. And we know that deionized water does have an ion concentration, measurable, 2 times 10 to the minus 7 molar in total ions. 1 times 10 to the minus 7 molar hydronium ion, 1 times 10 to the minus 7 molar hydroxide ion. But our handheld conductivity gadgets are not sufficiently sensitive to pick up those very small ion concentrations and show conductivity. So you took this deionized water, which shows no conductivity with our conductivity gadgets, and you put in some of the calcium carbonate, which you just made by precipitation, and you stirred it up thoroughly, and then you were asked to reobserve conductivity. What did you see when you reobserved conductivity? Did you get an on-scale conductivity reading? Nobody recalls doing this investigation? I think I'm going to make everybody take 2045 laboratory over and over and over until you remember what the hell you did in this course. One of these days, the administration of this university is going to understand me when I tell them this team stuff is junk. Everybody in that course should work on an individual basis, period. Then we'll find out whether or not you got something on the ball. Well, in any case, I'll fight with the administration later about this. You got an on-scale conductivity reading. It wasn't a large value, but you still got an on-scale conductivity reading. What did that tell you? The fact that you got an on-scale conductivity reading. Did some of the calcium carbonate dissolve? Yes. You're damn right. Well, then it happened spontaneously, didn't it? All you did was put the calcium carbonate in the water and stir it up a little bit. Which means pure calcium carbonate plus pure water. On this combination of materials, delta G is minus. Spontaneous. Now, why is it that the conductivity value you observed wasn't very large?
Because it's not soluble in water, it's only mildly soluble in water.
Not even mildly. Slightly. We know the solubility of calcium carbonate in water. Does 1.4 times 10 to the minus 4 molar ring a bell? We've looked at that data point quite a number of times in Chapter 19, analysis of various and sundry saturated solutions of calcium carbonate. The first one we looked at was calcium carbonate saturated in DIW. So the challenging aspect of this question is really, or the important aspect of this question is better, I should say, to get you to understand the difference between this term and what it means and this term and what it means. Because this is any imaginable set of conditions. And when you put together a pure solute with a pure solvent, when you put together sand with pure water, the only thing that can happen is dissolving. That doesn't mean much dissolves, but nothing else can happen except dissolving. And the dissolving proceeds until what condition is achieved? Equilibrium. Which means the solution is now saturated in solute component species. And that's when the dissolving stops. So does calcium carbonate dissolve spontaneously in water from a delta G0 standpoint? That means, can I make a solution in which I have both calcium ion and carbonate ion present, each at a molarity of 1? Hell no! Those things react, boom, and out falls calcium carbonate. And the calcium carbonate will continue to fall out as a precipitate until the calcium ion molarity becomes what at NLC? 1.49 minus 4 molar. Right? So, again, the benefit of viewing the term spontaneous from a thermodynamic standpoint, based on delta G0, I hope is now made to you more obvious. This specifies an exact set of conditions known as standard state. And now we got a specific handle on spontaneous. This, any imaginable set of conditions. So we proceed. Question 21-22. Just for fun. Are you familiar with two-phase changes involving the material water for which delta G0 is 0? There are not many transformations for which delta G0 is 0. Of course, delta GR being 0 means the system's at equilibrium. But we're talking about a system which is at equilibrium. Under what set of conditions? Standard state! On your paper right now, can you write the equations for the transformation reactions involving water? Two different equations for which delta G0 is 0. And in so doing, specify the conditions. These are the transformations. What conditions apply for this to exist?
1 atmosphere, 0 degrees Celsius.
P external equal 1 ATM. T equals
0 degrees Celsius.
All right, I'll write 273K. Since when we do thermodynamic arithmetic, we got to pay attention to T and Kelvin. Because, by definition, liquids and solids at this external pressure are, guess what? In the standard state. Remember that? Now, what about this one? Are you aware that this equilibrium condition can exist under a whole bunch of different conditions? What requirements for the components of this system must be met? Requirements for the components of this system. What requirements for the components of this system must be met in order for this condition to exist? You tell me and I'll write them down. Whenever the tendency for water liquid to evaporate is exactly equal for the tendency for water vapor to condense, this condition exists. And the weather folks call this condition what? 100% relative humidity. That's what the weather folks call it. Have you as yet experienced this condition in Florida? No. I'll bet you have. You get muggy, steamy days in July and August. This condition commonly exists after a rainstorm, for example. You're hot and gooey because as you perspire, there's no net evaporation of water liquid from your body surface. And evaporation is a cooling process because evaporation requires consumption of heat. And the water liquid which is in contact with your body gets that heat from your body and cools you off and makes you comfortable. But when that doesn't happen, you don't cool off. You remain gooey and sticky and uncomfortable. But we're asking about this condition existing in the standard state. Tell me, conditions. What pressure? If this air atmosphere right here, if we turn this room into a closed box and take out all the water vapor from the atmosphere, all the water vapor, I don't care if you apply a pressure of 1 million atmospheres. You can't make any water liquid because there ain't no water vapor present from which to make that water liquid. So what condition for water vapor must exist for this to exist under standard state conditions? What's this got to equal? 1 atmosphere, that's right. Which means the vapor pressure of this has got to be 1 atmosphere. At what condition does this exist? Come on, you know this. Right? Can this condition exist at 375 K? The hell it can't. Open up chapter 21. Let's go. Notes. Look at the vapor pressure data table for water liquid. Near the beginning of chapter 21. Immediately following the phase diagram. I think it immediately follows the phase diagram. You see the table I'm talking about? Page 21.5. Do you recognize that any temperature above 373 K, the vapor pressure of water liquid is greater than 1 atmosphere? The table tells you this. So if I have this water liquid at a temperature above 373 K, and above the water liquid is water vapor, and nothing but water vapor, and I squeeze so as to apply a pressure of greater than 1 atmosphere, then I can get this to exist. You can make this system. Just take a piston cylinder gadget. Water liquid. Nothing but. And now heat it up. What's going to happen? going to evaporate, isn't it? And the piston's going to go up. And what's going to be above the water liquid and below the piston? Water vapor. There's nothing else in there except water. Right? And that piston is going to keep going up inside this cylinder until what condition exists? This. And if you jack that temperature above 373 K, you're going to have to apply a force to the handle on the piston such that the pressure of the water vapor contained inside the piston cylinder exceeds 1 atmosphere and exactly counterbalances the vapor pressure water liquid. And clearly, I'm sure you know, this can exist below 373 K. We just talked about it. All right. Now, to move along. From this relationship, it follows that if we're at equilibrium, the reaction quotient is equal to K. And if we're at equilibrium, the change in free energy is how much?
0.
Nothing. Which means at equilibrium, this relationship exists. Damned important relationship. Because measuring delta G0 values directly for a reaction is very problematic, to say the least. I don't really know how you can do it. There may be ways. I haven't paid attention to it. You're looking at delta H0 minus T delta S0. You could measure the delta H0 without too much difficulty with calorimetric measurements, the likes of which you talked about in 2045. But how the hell do you measure this delta S0 directly? It's not easy to do. But notice that. Measuring K, that's not difficult to do. All you do is put together the components of a reaction system, both reactants and products, and let any reaction take place, either right to left or left to right, until what condition exists? Equilibrium. And now when it's at equilibrium, you can sit down, have a sandwich and a beer, take your time. Because when this thing's at equilibrium, its tendency to change into something else is what?
0.
Nothing. You take your time. No more kinetic difficulties. No more worries about the composition of the system changing. I mean, there are some cases where you'll have to keep the system in a closed box for equilibrium to be maintained because gases are involved. But no gases, who cares? And get in there with your measuring tools and determine the concentrations, if we are doing a solution study of products, and concentrations of reactants, and there are many straightforward ways to do this, and put them in our K expression and calculate K. And now we get delta G0. Because we know the temperature at which we run the reaction. R is nothing but a constant. And for this calculation, you want R expressed with what units? You remember in Chemistry 2045 when you talked about gases and gas behavior and gas laws? You usually use R with the value 0.0821 liter atmospheres per K mole. Remember that? Liter atmospheres. What kind of a physical quantity is liter atmospheres? Is it a force? What is it? Liter atmospheres. What is it? You did this in 2045 and you didn't know what the hell you did. So I'm telling the 2045 people, what you're doing isn't right, because these people are not understanding. All they're doing is taking stuff and shoving it into numbers, into equations, pushing buttons on his damn calculator, and then filling in the right circle on the answer sheet. And where's the understanding? Zip, it hasn't been established. Liter atmospheres is an energy unit. How about that? Volume times pressure is energy. If you don't believe me, do the analysis yourself. I once had a physical chemistry class taught me when I was working on my master's degree at little old University of Toledo in 1966. The instructor gave us an assignment which involved understanding the difference between collision theory and transition state theory, a kinetic issue. I read it again, thought about it, read it again. It just didn't come clear to me. So when we reconvened for the next class, he asked, "Do we have any questions?" I said, "Yes, sir. Would you please provide me explanation on this consideration you asked us to make, because I don't follow it from what the textbook has to say." He opened the textbook as he stood in front of the class. He opened the textbook, he looked at it, he looked back at me and he said, "This is clear to me," and went on. I didn't like this person too much. In any case, he gave us a homework set where we had to calculate a bunch of activation energies, since we were talking about kinetics. I calculated every damn one of them in liter atmospheres. He took off half credit. I said, "What's wrong? These values are all correct and they're in an energy unit." I know what bothered him, and I did it on purpose. To find out that my answers were correct, he had to do some arithmetic to convert my answers in liter atmospheres to his values in calories. Because those days we used calories rather than joules. He took off half credit, but I got a little bit of blood from that bastard. You see? I too was a student. And when I'm with somebody who's supposed to be a teacher and makes it clear that he or she has no idea what the hell this word means, I get mad. And I rebel. Because when understanding doesn't come across, I don't know what the person in the class is doing, but teaching ain't it. Now then, we talked about one of the valuable significances of this relationship. By getting K, we can get delta G zero values. We'll see more about this relationship and its application in the next chapter on electrochemistry. But we're now going to use this relationship to do a thermodynamic analysis, which I said we were able to do. First of this system, and then do you remember this system? Remember that one? We're going to analyze this system too. Now then. Ooh. Enough chalk on there to start my own chalk factory. If you crack open the data table, table 1, end of chapter 20, you can get, or you will see, the delta H sub F super zero values for this stuff and this stuff and this stuff. And you'll also see the S0 values. Tell me, for which component of this system do you think you'll see the largest S0 value? Well, first let's ask between these two. Do you think S0 is bigger for this or bigger for this? Which one? These are both ionic solids. For which of these will I see the bigger S0 value?
Calcium carbonate.
Calcium carbonate, why? What does S0 depend on? That's where the understanding lies. That's why we told you this before. What? Structure. They're both ionic compounds, so in that respect they're similar in structure. Phase, they're both solids. Temperature, they're both at 25 centigrade for these data, because they're all cited at 25 centigrade. And formula mass. Calcium carbonate has a much higher molar mass than calcium oxide. So you'll see the higher S0 value for calcium carbonate. But I asked, which component of this system do you think has the highest S0 value? You can look at the data. What do you think?
Each solid or including the carbonate?
All components. This. Two solids, and this stuff is gas. And entropy likes this gas stuff, doesn't it? Will you be surprised then to find out that even though CO2 has a smaller formula mass than these other materials, components of this system, this has got the highest entropy? You wouldn't be surprised. Good. And you won't be surprised, and you'll be right. Okay? In any case, with that information, we're going to calculate delta G0 for this reaction. And with this relationship as a given, we'll calculate K, the equilibrium constant. Tell me, do you think for this reaction as written, delta S0 is plus or minus? One mole solid becomes 1 mole solid and 1 mole vapor. So not only are you increasing the number of particles in the system, and entropy says, yeah, I like that. One of these things is gas phase. So you can bet delta S0 is for this. At 25 centigrade. This stuff look stable?
Yes.
Gee, I hope so. I'd be really upset if my calcium carbonate spontaneously fell apart. I wouldn't have any chalk with which to write. Well then, do you think this stuff is decomposing spontaneously from a delta G0 standpoint under these conditions? No. But we said delta S0 says yes. So what thermodynamic factor associated with this transformation is keeping this stuff stable?
Temperature.
It's on the board. Delta H0. Delta H0 is a large number and plus or minus?
Positive.
Plus, you betcha. Because this is a net bond disimprovement process. You look at the numbers to get delta H0, delta S0. I'll write down the values. If, in accord with delta G0 equals delta H0 minus T delta S0, and operating at 298 K, we calculate delta G0, we'll get plus anti-spontaneous, or at the minimum, non-spontaneous in the direction written. 129.0. And I wrote at 298K because you know delta G0 is a temperature dependent term. So when you write down a delta G0 value, you should say the temperature at which the value has been calculated or observed. Now then, K. Before we evaluate K, because now we have what we need to evaluate K. What is K? Write K for this transformation. Write it. Write it on your paper right now. Do you remember that? Thermodynamically, if a gas is part of an equilibrium system, you are to refer to that gas in terms of partial pressure. There's K. Nothing to it, right? This is a solid. That's not involved in the contained in the K expression. So is this. So there's K, partial pressure of CO2. Now then, let's do the arithmetic. What are you going to put in for R? You're going to put in 0.0821 liter atmospheres per K mole? You can put that in, but you'll now have a unit mess. You want R in what units? Never mind the number. Kilojoules or joules. That's right. 8.314 joules per K mole. There's the R value we'll use. And this stuff, as you likely have noticed, is on the information sheet. So is that relationship. I don't hold you responsible for memorizing this stuff, but I do hold you responsible for being able to use it. But you already know that. This grinds to minus 22.64. Why did I do this arithmetic? So as to have two digital entries past the decimal point. Or put another way, with the arithmetic that I have done, I may now legitimately express my equilibrium constant value with how many significant figures? 2. Because that's a log. And the minus 22 part is the characteristic of this log. These digital entries correspond to measurmental significance. These digital entries, which are part of the mantissa of this log. Okay? Now, I'll take the analog of this value to get K. In so doing, I get 2.3 times 10 to minus 23. Now, this brings us to another consideration. By rigorous definition, and it follows from this calculation. You see from this calculation all the units go away? The equilibrium constants don't have units. But all along we have used equilibrium constants as if they had units. Because if you're going to treat equilibrium systems from a practical standpoint, in order, for example, to calculate equilibrium concentrations and equilibrium partial pressures, you better apply units. So what unit should we apply? What unit should we attend to this equilibrium constant, which numerically is 2.3 times 10 to the minus 23? What unit or units should we apply? What is the equilibrium constant? It's the partial pressure of CO2 gas. Period. End of story. And partial pressures are going to be expressed in what units?
Atmosphere.
Atmospheres or bar. We'll use atmospheres. Statement, which we've just demonstrated. Whenever you calculate an equilibrium constant from thermodynamic data, which we just did, which we will do for this reaction, you will always get a unitless quantity. But for any practical applications of equilibrium constant, like calculation of equilibrium molarities or partial pressures, you must attend units to the equilibrium constant. Where are you going to get these units? Where do the units come from? What are the units for this reaction? Atmospheres to the minus 1. The units on K, if we need them, come from the equation for the reaction and no place else. So with that, we're going to jump to question, and we'll go back to this in a moment. But right now, I want to jump to question 36. See question 36 on page 2116. Here's the question I tell you to do, because it will parallel directly our analysis of this calcium carbonate decomposition process. You see the question to which I refer? The decomposition of 1 mole of aluminum sulfate solid into a mole of aluminum oxide and 3 moles of SO3 gas. For that system, if you answer this question, you will get out table 1 and get the thermodynamic data for the components of that reaction system, and you will calculate K after having calculated delta G0. What are the units on K for that reaction? The one I'm now asking you to look at. What? Atmospheres cubed. So if, for that system at equilibrium, you want to know the partial pressure of SO3, what are you going to do? You will have calculated a K, which unit-wise is in atmospheres cubed. What will you do for that system to get the partial pressure of SO3 at equilibrium? Take the cube root. Let the units talk to you, and you win. Now then, back to this. What does this mean? Let's write down significance. What's the significance of this? I'm referring to questions 29 and 30. Chapter 21, of course. We want to know the significance of this value. There's another one of my brilliant Van Gogh quality sketches. For $1,000, I'll autograph this for you. experiment. We take a 10-liter flask, stopperable 10-liter flask, off the shelf. We investigate the contents of the flask to be sure that within the flask there are no CO2 molecules. None. I don't care about oxygen molecules. I don't care about nitrogen molecules. I don't care about argon or helium or hydrogen. I just don't want any CO2 molecules in this flask. And then I'm going to introduce into this flask this stuff. You know, this stuff. Chalk. I'll put chalk in the flask. Powdered calcium carbonate. Doesn't have to be powder. What's going to happen? What will happen regarding the calcium carbonate? Will the calcium carbonate, under these conditions, spontaneously decompose? The hell it won't. It will spontaneously decompose until the partial pressure of CO2 developed in the flask is 2.3 times 10 to the minus 23 atmospheres. And then the decomposition shuts down. Because then, and only then, are you at equilibrium. Right? Just like the calcium carbonate stuff we talked about before in water. Q. How many moles CO2 at EQ? And how many molecules? How are you going to calculate moles? PV equals nRT. We know P, pressure for calcium, for CO2. There it is. We know V, it's 10.0 liters. We know R, in this case we want 0.0821 liter atmospheres per kmol. And we know T. We're doing this at 25 centigrade. And after you calculate moles, how do you calculate molecules? Avogadro's number. We'll pick it up from this point next time.